Okay students, welcome back. So, we are basically discussing functional group based strategies, and we have discussed that how you can use several synthetic equivalents. We mainly talked about how formyl anions are chosen as a synthetic equivalents to introduce a CHO functional group in couple of molecular structure. So, we will try to continue our discussion on the same point. Now, here today the initial problem which we will try to focus, it is based on little bit different thing. See the structure very carefully, then we will try to give you that how this molecule can be constructed. Now, this part, this molecule is having a 3 substituted furan, is a furan, okay, is a furan ring, and here this is a bicyclic compound. So, it is having a ring A 6 member, ring B 5 member, okay. And obviously, I will give you the starting material. I say the starting material also will be given to you. The starting material which I have given to you, it is a this starting material which is not very popular starting material, and the other starting material which I say is given to you a furan based compound. Now, as the starting material was given to you, your job is almost simplified. Starting material 1, starting material 2. Now, you try to correlate that how this 2 starting material can be assembled, or how this target can be skeletally disconnected, so that 2 of the starting material can be arrived. Now, we will try to do a retro pathway. We say this molecule, as it is having a alpha beta unsaturated, or not exactly alpha beta unsaturated, it is this part is alpha beta unsaturated. So, we can basically construct through a intramolecular aldol dehydration, which is always our preferred pathway, and the disconnection should now give you 1, 2, 3, 4, a 1,4 dicarbonyl species, where the remaining part of this molecule will be similar. So, we just disconnect it here, and we say this is a goes to a intra aldol. Now, we say that this carbonyl adjacent to a furan system as well as adjacent to alpha carbonyl can undergo this intramolecular aldol. Now, see the starting material which was given to you. The starting material which was given to you, now basically we are trying to figure it out how this starting material can be assembled to give you the required target. Now, I said Neff reaction is known to you, fine. So, if you do a Neff reaction here, you get this carbonyl. So, particularly this disconnection was done with this Neff transformation. Now, we are almost very close, and now you see if you have this starting material with the furan part CH2, CH2, NO2, we say the carbon ion can be easily generated to undergoing a Michael type of reaction, is not it? Now, in reality, in terms of synthetic equivalents, probably this reaction, what synthetic equivalents we have used? We have basically used a synthetic equivalents something like, if you now do a disconnection here, you see that we have used a synthetic equivalents, this synthetic equivalents, which is basically adding here, is not it? This is basically adding here to give you CH to CaO, and the remaining part might be similar. Now, so this synthetic equivalence which is coming from a this nitrobasis through a Neff reaction, which you already talked about. So, now you go to the forward synthesis pathway and you find that this is a very excellent demonstration. I will give you a home assignment, that how the starting material you can synthesize from cyclohexanone, how this compound you can make. Okay, now, coming to our problem, we react this compound with a starting material which is available to you in this form. And now, we say that if you observe the target molecule, we are basically using this CO as a synthetic equivalence and trying to put a Michael reaction with this CO minus here. So, this CO, this C double bond O is undergoing a Michael reaction here, is not it? Is undergoing a Michael reaction here. So, this is the synthetic equivalent which is really coming from this furan derived nitrospecies. So, this nitrospecies now reacts here in a Michael fashion, and then you do a, I write Michael followed by Neff, both are done together. So, what basically you will get? You basically get is not it? Now, I will now show you what exactly the synthetic equivalents we have used here. Now, do a disconnection here. The synthetic equivalents what basically we have used here is not it? This synthetic equivalents which is basically a D1 species, D1 species which we used here. Now, as I said, this is not commercially available. This we have been generated with the help of this nitrospecies, and thanks goes to the Neff reaction. We know that C nitro bond can be cleaved to corresponding and can be converted to corresponding carbonyl compound with the help of this Neff reaction. So, we can start with the starting material with the help of a synthetic equivalent something like this, and then you simply do a aldol kind of dehydration. So, this is a complex synthetic equivalence, and in terms the entire this starting material can be now figured out as a synthetic equivalence of this species. Yes. So, this is the real intermediate, and this is the reagent which is acting as a synthetic equivalent of this particular species. So, your synthetic equivalent based problems can be solved in this way, and always a skeletal disconnection is pretty much required. Next one we will try to explore a similar kind of problem, but this is bit unusual. We will be using a functional group interconversion using a umpolung species. The target molecule which was given is this one. It is a alpha beta unsaturated ketone having one end having a O methoxy. The starting structure or precursor which was given to you cyclohexanone. Now, we try to correlate what are the extra functional group was added to the compound. Starting material is this one. You have added a extra COMe group, is not it? COMe group, and then you have added extra O methoxy here, Now, what is said that okay, you have the starting material. So, you basically need to add COMe. Now, the COMe, it could be a positive COMe or could be a negative COMe, means a MECO minus, a acyl anion or a acyl cation. So, this is the acyl anion which is the umpolung. Now, if you see this compound is basically is a Michael acceptor as a 1,4 as well as is 1,2. So, this molecule can only accept, okay. There is no donor site except this one, but this synthetic this part probably is untouched, because if you see this 1, 2, 3, this CH2, this 3 CH2 remains untouched. So, probably you need some kind of this COMe species which attack either 1,2 or 1,4 fashion. We will try to figure it out how it takes place. Now, the COMe species, you can basically generate from a acetaldehyde which is protected as this 1,3-dithione. So, you pick up this hydrogen by a lithium and now react this species with this cyclohexenone in 1,2 fashion. So, basically you will get a compound whose structure will be this, a methyl is there, this is the thing. Now, what is said, your COMe addition somehow was done, but only thing is your double bond was kind of a migrated or rearranged with the insertion of a O methoxy group. We will try to figure it out that the sulfur will be not there. We will make sure that first the sulfur goes up. So, basically you get a OH COMe with this compound. Now, actually reality on this mercury mediated 1,3-dithione deposition was done, methanol was used as a solvent. And as mercury was still there, this starting material seemed to have a intermediate which basically chelates with this mercury through this alcohol oxygen as well as this carbonyl oxygen. Okay, we will draw the structure more clearly in the next slide or next piece of paper. We say once this 1,3-dithione group deprotect, you basically have a compound something like this, and the mercury was forming a chelate, a 5-member chelate or chelate, and then your double bond is here. Now, this methanol is basically acting as a nucleophile. Now, as this chelate was done, the electrophilicity of this center was correspondingly enhanced, and then methanol was attacking in a kind of a Michael fashion, not exactly Michael fashion, and that basically triggers up the elimination of this water molecule with this OH and this H. So, basically is kind of a methanolysis takes place, and then you see this compound will basically generating a methanol O methoxy attacks here, and this hydrogen and this OH goes up as a water. So, basically you are having a nucleophilic attack of methanol, and now the target which was initially given to you is these things. The starting material which was also given to you is a cyclohexenone. So, what exactly we did? We just do a acyl anion umpolung chemistry. Now, this acyl anion umpolung chemistry was normally first reacted in a 1,4 fashion. Now, this 1,4 fashion, sorry 1,2 fashion, 1,2 fashion, the 1,2 attack was done here, and then once this 1,2 attack was done, then this tertiary alcohol was reacting with this mercury which was used for the removal of this 1,3-dithiene, and then methanolysis takes place. Methanol basically attacks here, methanol attacks here, this allylic double bond basically migrates. So, this is the main synthetic transformation, and you actually need a MECO minus which has been generated from this particular acetaldehyde 1,3-dithiene. It is bit unusual to visualize, but sometimes it gives you a very nice interesting chemistry. We will just try to have little bit more example on this umpolung species. What we say that is this species are basically a D1 species or a 2D1 species. Next, we will talk about a problem which will basically highlight that how this umpolung chemistry was used in the synthesis of some natural products. This particular compound is a natural product, its name is E-cyclanthone. It was used as a pheromone. Pheromones are basically chemical compounds which have been secreted by some certain insects, and they are acting as a chemical messengers which helps them to communicate with two insects or two primates. They are basically secreted by those insects, and they have a strong aroma. These compounds are volatile in nature, and they are acting as a chemical messenger. So, you have to talk in the chemical way, you secrete some chemicals which then gives the signal. Now, this particular natural product or cyclanthone will now do the retro. The starting material was given to you for your analysis. I said the starting material which will be provided to you is this one. Now, as I am doing a functional group based approach, so it is the starting material having a allylic bromo, and the final target having a carbonyl compound as the main core functionality, and two olefinic bonds are there, but the starting material two olefinic bonds are also there. So, these two starting olefinic double bonds remains same in the target molecule. So, no need to change anything because methyl is there, only thing is this CH2 is there. So, up to this part 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, up to this part the starting material is providing to you. You basically need to add this entire part to your starting material to access the target molecule. Now, if you see this allylic bromide can be a very good electrophile, is not it? Now, if we do the retro, we say that we will make this connection here. So, basically you can think about so, if you having a this synthetic equivalence and your starting material was available to you is a simple electrophile, you can easily construct a carbon carbon bond. Now, this particular synthetic equivalence is basically a D1 species it can also be further electrosynthetically disconnected as discussed earlier by this bond. So, this is a 2d1 species, means this end is 1d1, this end is 1d1, and this is your one electrophile, this is your one electrophile which has been supplied to you. So, in principle this molecule which was given to you, will now write the molecule in a different way. We say this molecule can be simplified as R prime. Now, this part is the R, I say, and this part is the R prime. So, this connection now can be basically based on a minus which is a R plus and R prime plus. So, it is basically a electrophile, both the things are electrophile. So, what you need to do? This is a D1 and this end, D1 at this end. So, altogether this is a 2D1 species. So, now finalize the end game of the synthesis. Now, we will start from a starting material which is already known or available to all of us, formaldehyde 1,3-dithiene. As a first we will do a LDA 1 equivalent and we use a isobutyl iodide and then do a mercury plus. So, initially we will basically get this isobutyl CHO, or other way you do not put the mercury here, you first do the synthesis like this, you put this, keep this hydrogen, now put another equivalent of LDA and your another electrophile which was given to you, which is having this structure. So, then you will basically get sulfur and then your these things. So, now you simply do a Hg2 plus to close the final synthesis, does not it? Or if you have started the earlier way, formaldehyde 1,3-dithiene, LD 1 equivalent isobutyl iodide, Hg2 plus, you end up with here. Now, here you react with again 1 equivalent of formaldehyde 1,3-dithiene to get this isobutyraldehyde 1,3-dithiene, abstract with 1 equivalent of LDA and react with this, you end up here and then do the mercury mediated reproduction. So, by this way, this kind of synthetic equivalents will always help you to give you a very nice flavor. Now, we always talked about this dithiene chemistry. Now, are there any other ways to generate this kind of species? I said this is a nice equivalent of formyl anion. Now, if I talk about a acetyl anion, what are the species you can think about? This is already known that this species you can use it. Now, in this case is quite fitting tribute to remember a great organic scientist named Gilbert Stock. Now, Gilbert Stock was using this chemistry of O protected cyanohydrin. What is this? If you have acetaldehyde, you react with HCN to get this corresponding cyanohydrin. Okay. Now, cyanohydrin, as I said, they are very unstable. You protect this cyanohydrin with a selectively protecting group TBS chloride or this free alcohol. So, this alcohol is now protected as a O TBS CN. Now, this compound is now named as methyl OTBS CN. It is called O protected cyanohydrin, O protected cyanohydrin. Now, this compound, if you treat with a base, cyanide is electron withdrawing group, you basically get a minus here OTBS. Now, this compound now act as a umpolung, and here now if you react with a electrophile like cyclohexanone, initially basically you will get O minus CN methyl your OTBS. Okay. Everything is fine. If you just put a quench with simple methanol, you will get a OH plus also. Now, this oxygen silicon bond can be normally clipped, and here this oxygen silicon bond was normally clipped by some silicon some fluoride species, and then that basically keeps in this way and gives you this. So, in reality at the end you basically get a this compound. Now, what is this retro? This retro is nothing, a carbonyl plus a acyl anion. So, acyl anion has been really generated from a O-silyl protected cyanohydrin, which is also earlier used very much, and Professor Gilbert Stock was the main pioneer to invent of this O-silyl protected cyanohydrin, and normally this is also a very good source of umpolung in addition to your conventional 1,3-dithiene reagent. So, probably next week we will be talking about something else. So, synthetic equivalents, this is the very preliminary discussion we have covered. We will try to cover more of synthetic equivalents when you talk about a condensed lecture on synthetic equivalents in the final part of our discussion. So, till then goodbye, have a good time.